Welcome to this video. I will explain the vision transformer architecture via reading the paper, an image as well as 16 by 16 words, transformer for image recognition at scale. This paper was first published in the conference ICLR in the year 2021, so we have to keep in mind that's already 4 years ago. So let's just start with the abstract. While the transformer architecture has become the de facto standard for natural language processing tasks, its application to computer vision remain limited. So, in the natural language processing domain, we already had the paper Attention is All You Need, where the attention modular was introduced and got famous, and then all the natural language processing tasks are using more and more have used more and more like architectures with attention or will transformer modulars. This is different to the computer vision domain in year 2021 because in the year 2021 we still just used CNNs or a combination of CNNs with a little attention blocks, but not a transformer block itself. So the authors are saying when pre-training on large amount of data and transfer to multiple mid-sized or small image recognition benchmarks, vision transformer attains excellent results compared to state-of-the-art convolutional neural networks. So what they achieved actually, they achieved that the vision transformer achieves good results on the vision benchmark. They pre-train it on ImageNet, Cypher, and VTAB, and it's similar performance as the CNN architectures. What kind of CNN architectures? Stuff like ResNet or VGG, for example. Yeah. So let's jump into the introduction. The most important part here is actually this sentence: inspired by the transformer scaling success in NLP, so it was used in GPT and BERT, I already mentioned that. We experiment with applying a standard transformer directly to images. So no CNNs at all, just trying to implement the transformer on scratch on the images with the fewest possible modifications. To do so, we split an image into patches. We see this later. So an image, we have a big image, we split it up into single patches and then do a linear embedding of those patches as an input to our transformer model. And the model was trained with supervised training. So we trained the model on image classification in a supervised fashion. So we have just like ImageNet. ImageNet is more than a million of pictures, all with one label. So pretty basic. We have, I don't know, a man, or we have like a car, and the let's try to draw a car. Okay, so a car, and the model has to predict, oh, this one is a car, this one is a man, stuff like that. Okay, so this is how the model was pre-trained or trained. Yeah. And then when trained on, here it's now become very interesting. When trained on mid-sized data set, so not on very large data set, mid-sized data set such as ImageNet, without strong regularization. So when do we use regularization? Regularization was normally used to prevent the model from overfitting. This model yields modest accuracy of a few percentage points below ResNet of comparable size. So the model didn't achieve the same result as ResNet's, a little worse, but not too worse. And the authors are claiming, okay, this is as expected. Why? Transformer lack of some of the inductive bias inherent to CNN, such as translation equivalence and locality, and therefore do not generalize well when trained on insufficient amount of data. Okay, let's understand this part. So actually in the CNN architecture we have an inductive bias because our kernel just looks at the pixel at a local space of the image, and therefore we say that the image or pixel that are nearby other pixels are more important than pixels that are far away. So for example, look at this image. I don't know, we have here a sun and stuff like that, doesn't really matter. And we have a pixel on top here. And this pixel, with the CNN, we say, okay, this receptive field is most important for this pixel, and with the transformer architecture we have a global receptive field. We will see it later, but this means that this pixel can see every other pixel, and so the pixel has to learn, okay, the most important pixel are maybe nearby, and we didn't have this inductive bias already implemented in the vision transformer, and therefore we have to train it from our dataset. And if the dataset is not large enough, it's hard to learn this inductive bias. Maybe a cool thing is if you heard about the beta lesson of AI, it's called beta lesson of AI. There the idea is that we try to implement as few as possible inductive bias into our model, and let's just learn the model should learn the architecture or the key idea of our data with the data itself. So it's the idea is that we are not as a builder or as an AI engineer try to bring the knowledge from the domain into the model, but we make the model as general as possible, and then use a lot of data in order that the model can learn rules for itself for the data. Okay, so you can just Google at beta lesson and you find this blog article. I really highly recommend to you to read this one. And now they are saying, however, the picture change if the models are trained on larger data sets. So if you have larger data set, we find that large-scale training trumps inductive bias. Our vision transformer attains excellent results when pre-trained at sufficient scale and transferred to tasks with fewer data points. So what does it mean? If we have really large data set between 40 million and 300 million images, we solve this issue with the inductive bias. The transformer can learn it from the data itself, and then the results are getting pretty good. This figure 1, we can see the overall overview of the vision transformer. And as the author said in the introduction, the image is splitted into singular patches. We can see it here. We have one image, and this image is, for example, splitted here into 9 patches. And each patch now corresponds to a flattened vector. So this vector or this patch has a size of 16 by 16 pixels. Okay, so and this is why if we look back at our title of the paper, this is why the authors are saying, okay, an image is worth 16 by 16 words, because normally in the language domain, one token can correspond to one vector can correspond to a token or to a word, and here 16 by 16 pixels corresponds to one word or one token. Okay, and then we do a linear projection of flattened patches. So what does it mean? Let's look at here. So we have our matrix 16 by 16 pixels, and we now flatten this matrix into just a normal vector, and now we have a vector with a length 16 times 16. So this is, we can multiply this and then we get the length. And now we do a linear projection in a higher dimensional space, so we get an embedding dimension. So let's do it like this. And we have a weight matrix. We can call this one just W, and W is our weight matrix, and every vector is multiplied by this weight matrix in order to get our patch embedding. So what does it mean? If we take this patch in the top left corner, we will multiply it with W, and then we take the next patch and also multiply it with W, and then we got this tokens here, or actually it's this token. So we get this token, and now we have to add a positional embedding. Positional embedding, we need to do this because the transformer can't can't find out where this token comes from. So if it's in the top left corner or top right corner, the transformer without the positional embedding can't know this. This is why we add a positional embedding. In this paper, the authors didn't use a rotary embedding or sinusoidal embedding. They just use a learnable embedding, positional embedding. So let's just have a look how the learnable parameter embedding looks like. So we have here our patch embedding, and we just add a positional embedding. For example, for position 1, and 1 is in our example here in the top left corner. And now this one is at the beginning of the training, is initialized completely randomly. You can just use NN parameter in Torch, and then we update this positional embedding with gradient descent, and so the model can learn the positional embedding over gradient descent, and we didn't add any inductive bias with the positional embedding. We just say if you want to learn that the position is important in a picture, so where the token is, you can learn it by yourself via gradient descent. Okay, we are doing this for every single patch. So we have in this example we learned 9 patch embeddings. Just cleared a little bit this figure, and now we look at this token, and this token corresponds to the class embedding. So we add one token, and this token tries to extract all the features from the other tokens that are important in order to make at the end the classification if on the picture is a car, a ball, or a bird here, or any other class. So we add a token which is always the same for every picture, but we learn it, and this token can correspond to all the other tokens via normal attention and can extract the important features of those tokens in order to make a decision. So this transformer block takes as input all those tokens, and we can see the transformer block here on the right. I will not explain how the multi-head attention works. I think that if you see this video, you already should know how the multi-head attention works. If not, I will maybe do another video about the multi-head attention. But we see we have the embedded patches, we do normalization, we have the skip connection, we don't use any masking or stuff like that. And yeah, we use this encoder blocks like n times. And then the most important part, at the end, we got at the end of our last transformer, so if we do it 6 times, we have like 6 transformer blocks, and then we have this output again here. So let's do it like this, you know. So we have like a 9 tokens, and token number 0 corresponds to our class token, and this token has to learn from all the other tokens which the most important feature in order to make a decision which class this picture is. So we just extract the last token, this one, and put it in an MLP. So we have the class token at the end. We put it in an MLP, and then we do a classification over all our classes. So for example, if we have like birds, car, and so on, and here we have, I don't know, we could say mountain or stuff like that. So this way, oh, this looks a little, okay, let's do it like this. We say cat, and here we can write dog. And so we take the last class token and make a prediction with a simple MLP. So not a huge MLP block, just a simple MLP block that maps from the model dimension into the class dimension. And then we get here like real numbers, we do a softmax over it, and then we train it with cross entropy loss. And that's basically all what the vision transformer is about. And yeah, I hope that it helped you a little bit to understand the vision transformer. And now let's just read this little section again. So we note inductive bias. We note that vision transformer has much less image-specific inductive bias than CNN, and CNN's locality, two-dimensional neighborhood, structure, and translation equivalence are baked into each layer throughout the whole model. In VIT, only MLP layers are local and translational equivalent, while the transitive attention layers are global. So what does it mean with the global? Here, at the first step of our transformer model, if we are here in the multi-head attention, each token can see every other tokens. So what does it mean? This image can look, or this patch can look at this patch there. And that's completely different to CNN architecture. CNN architecture always just can look locally. We can do a lot of tricks to make the receptive field larger, but the transformer is very cool because we have like the global receptive field at the beginning. Okay, so let's continue here. The two-dimensional neighborhood structure is used very sparingly in the beginning of the model by cutting the image into patches and fine-tuning time for adjusting the position embedding for image of different resolutions. So yeah, what they are just saying here that there's a little inductive bias, but if you compare to normal CNN, it's yeah, much less. Let's have a look at the training of the VIT. We can see here different models. So we have like a model VIT huge, large, and base. We have 12 layers, 24 or 32 layers, and different hidden sizes. So let's just have a small recap. What does it mean? 12 layers. It's corresponding to those how often we are using the transformer encoder block again, so L times, and yeah, the smallest one using it 12 times and the largest one 32 times. Then we also have the hidden size D. The hidden size D is the size of our model, so we have our patch, and this patch we're bringing into a higher dimensional space with our weight matrix W, and this weight matrix is as large as this output, so as large as our hidden size D. Then we have MLP sides and heads. So heads is for the multi-head safe attention, and MLP size is equal to how large the MLP will be. I don't know if they're meaning this MLP or the MLP here, but it normally they're meaning this MLP because this one is pretty basic. So they're using this MLP, and yeah, most of the time it's a factor by 4. We can see it here. If we multiply this by 4, we are getting this MLP size, and yeah. So let's just have a look at their training. We train all models, including ResNet. So they're for their evaluation, they also train the ResNet, and they use the Adam optimization. So Adam always have 2 parameters, beta 1 and beta 2. It corresponds to momentum and the learning rate of a special learning rate for each parameter. We have a batch size of 4096, so pretty high I would say, and a weight decay of 0.1. So nothing special here. They used a learning rate and warm up and decay. So what does it mean? This just means the learning rate at first is low, then goes up and then goes down. Sometimes you use linear warm up, or you could use a cosine scheduler. It doesn't really matter. So for fine tuning, if you want to see the experiments, you can read it also by yourself. The most important part of the paper, I think, we spoke about. And then just to summarize it, we have a vision transformer. Now the transformer has a global receptive field with the attention. Each token can see each other token, and we add one class embedding. This class embedding or class token tries to extract the most important parts in order to make at the end the decision to decide in which class to put the image. And it was trained with cross entropy. Yeah, that's actually the most important part of this paper. You can find the link to the picture in the video description, and if you want me to read any other paper, just write in a comment, and hopefully we see us in the next video. Thank you.